Today we're going to look at two operations that can be done on vector fields, and those operations are called curl and divergence. Now, you can tell probably by the name of them that there's a lot of physical applications of these. There's a lot of physical significance to them. For our purposes in this class, we're really only going to focus on how to do the computation so that we can use it to do some other mathematics. But I'll give you a little sense of the physical application and point you in the direction if you want to learn some more. Okay, so the operation of curl, suppose we have a vector field with our standard notation like this. The curl is defined to be, we put in our vector field and we get out a vector. It has these partials, the z components with respect to y, the y components with respect to z. So just like when we talked about Green's theorem, I call those mixed partials. In fact, here are here's the combination that's in Green's theorem, but these have the other mixed partials too. P is x's component, so x's component with respect to z. R is z's component, so z component with respect to x. X component with respect to z, z with respect to x. So it's doing some sort of combination with those mixed partials. The divergence computation is if we have this vector field, we're going to take the partial with respect to x of x's component, partial with respect to y of y's component, partial with respect to z of z's component, and add them together. So those computations are very straightforward. We'll talk in a minute about what they mean and how we're going to use them. But first, focusing on the computation, sometimes this curl formula can be a little hard to memorize or to remember. Some people are perfectly fine with it, but there is a helpful tool I can use that might help you remember this formula. And that is if we use operator notation. So we've seen this before. We've seen it next to f. We've seen, the gradient of f. And that meant the partial with respect to x of f, partial with respect to x of y, partial with respect to x of k. It gave us a vector. If we just think of that part without the f and just look at that as an operator, that's called the del operator. The del operator is just a notational tool that says, think of it like a vector where in this component is the partial with respect to x. Notice there's nothing in it. Remember how I told you always have to have something in there? It's an operator. So by itself, this means nothing. It's telling us to do something. So when we put it up next to a function, it says take this thing here and put it next to a function. And even though this is not actual correct mathematics, it's a tool for remembering, think of it like you're multiplying. Okay, I even hate to say that because the mathematics is all about it, but you're doing this. So when I put that del operator next to f, I'm operating on f with each of those partials. Okay? It's just a tool for remembering. And the divergence, for the divergence of f, we would think, all right, we're going to take this operator, which are these partials with nothing in them, and we're going to dot it with f, and f we call p, q, r. And if you think of this like a regular dot product, even though this is not officially a vector, but if you think of this, we would multiply these two. Okay, so you can't actually multiply those. This has no meaning by itself. But if I put them together and thought of the meaning of partial of p with respect to x, that's what we're going to do. Think of multiplying these. That's not really the real operation, but partial of q with respect to y, and these last two, partial of r with respect to z. So again, it's just a tool that helps us remember the formula. Now you probably don't need any help remembering either of these formulas. They're pretty straightforward. But if you want help remembering this formula, notice that we can think of curl as taking that operator and crossing it. Now this kind of makes sense. Dot product gives me a scalar. The outcome of the divergence is not a vector, it's a scalar. The outcome of the curl is a vector. The outcome of a cross product is a vector. All right, so watch how this would work. I, J, K, the del operator would be partial with respect to x, partial with respect to y, partial with respect to z, and then F is P, Q, R. So this was our tool for remembering how to do cross products. So now if we're going to do this like a cross product, we're going to get I times this product, but we're not actually taking a product. We're going to take the partial of R with respect to Y minus the partial of Q with respect to Z. Okay? Partial of R with respect to Y minus the partial of Q with respect to Z. Minus the J component. For J, we're going to take, think of this product minus this product. Technically not a product here, but partial with respect to x of R. So partial R with respect to x. Partial R with respect to x. Minus partial of P with respect to Z. Plus K times dot, dot, dot. I'm not going to fill in the rest of that. But notice, RYQZ, RYQZ. RXPZ, well, this is backwards, RXPZ. Yeah, but I have my minus out in front. So if I incorporated it in, it would be PZ minus RX. And if I had gone ahead and done the last one, this is what I would get. Okay, so that's just a tool to help me remember the formula, how to find that curl. All right, so suppose I asked you on this problem here to find the curl. So the curl of F, I like to use the whole cross product idea instead of that formula. Partial with respect to x, partial with respect to y, partial with respect to z of yz, xz, xy plus 2z. Okay, so for this cross product, for the I component, we're going to take the partial with respect to y here, which is x, minus the partial with respect to z here, which is also x, so x minus x. And then the j component is negative, and so for the j component, think of crossing out this column. We're going to be taking partial with respect to x here, which is y, minus partial with respect to z here, which is y. And for the last component, the z column, we're going to take partial x here, which is z, minus partial with respect to y here, which is z. That doesn't happen very often. I picked a great example there. I got 0, 0, 0. So that is my curl. It is a vector. Okay, so I happen to get the 0 vector. But that's how we compute curl. Now, by the way, we found out back in the last section that if px and qy are equal, we called those mixed partials, then in 2 dimensions your vector field is conservative. And then I pointed out this homework problem to you, and I said when we extend to a vector field of 3 variables, that we have each 3 of these pairs equal, then that vector field is conservative. But if you look back, if you flip back a page and you look at how the curl is defined, this is the z component of the curl, and you have your x and y component of the curl is one of these minus the other. So if they are equal to each other, you are going to get a curl of 0, 0, 0. And so it turns out that if that curl of your vector field is 0, and you have continuous partial derivatives, so there is that part as well. But if the curl is the 0 vector, f is conservative. So this is actually going to be our test for whether or not our vector field is conservative in 3 dimensions. So this particular vector field that I wrote down just so happened to be conservative. So that is going to be a test we can use for a conservative vector field. All right, that's all that we need to get from this section. We just need to be able to compute these because we're going to use them in theorems for work integrals and flux integrals in the next 2 sections. But I want to give you just a little idea about the physical significance, and I'm just very much going to paraphrase it, right? So the idea of curl has to do with the idea in our vector field of if we have rotation. So, when we have something going on like this, and we think of the vector field as rotating around a given point, that is curl. So if we have a large vector field, at any point in that vector field, if we were to drop a little leaf in there, would it spin that way? Would it spin the other way? Would it not spin at all? And so that spin would be different at anywhere in that pool of water. The amount the tendency to spin or rotate at any given point, that's called the curl. So here, if the curl is 0, we would call that vector field irrotational. It's not rotating. All right, so that's curl has to do with spinning, with whirlpools. Now, that's very, very simplistic. Curl has actually got a lot more going on than that. And there's some really excellent videos. If you look at my 5C page, if you want to learn more about curl in applications, it's pretty cool. There's one where they have this little disc floating down a river, and you see how it spins some ways and then it spins the other way, and they talk about the mathematics behind it. So a lot going on there. We're not going to delve into it. Okay. Divergence. Oh, I didn't even compute the divergence here. Let me come back up there and do that. The divergence of f for this example, you can go ahead and think of it as del dot f. I usually just think of it as it's the partial here with respect to x, here with respect to y, here with respect to z. What I have to remember to do is to not make a vector out of it. We're not taking a gradient. Partial with respect to x of that first component is 0. Partial with respect to y of that second component is 0. Partial of the third component with respect to z is 2. And so the divergence of f is 2. It's going to be a scalar. It might not always be a constant. It might be like 2x or something like that, but this will be a scalar. This will be a vector. And by the way, this vector might be in terms of variables. This is just a sort of a simplistic example. We'll see some more complicated examples. But what the divergence physically is measuring is the tendency of our fluid or electricity or whatever we're measuring at a given point to move out from that point. So if we have that our flow is out of our point, the divergence is positive. So this is measuring the tendency to flow in or out of a given point. If we have flow going into that spot, then the divergence is negative. Okay, so if it's positive, it's flowing out from that spot, maybe that's a source of water, maybe a faucet's turned on there. If the divergence is negative and maybe it's all coming in, maybe that's a sink or a drain. Okay, sometimes we have spots where we have both fluid flowing out and fluid flowing in. Then what the divergence measures is the net. Like this particular one, there's more out than in. So the net is more out than in. Out gives me a divergence which is positive. Okay, so lots more you can learn about that. One thing I wanted to show here, I can't do it in a video. It doesn't trap. It somehow this doesn't capture when I do animations, but you have access to this from the 5C page. If you go to CalcPlot 3D, there's a link on the 5C page, and then you go over here where it says Add to Graph, select Vector Field. Okay, I just let it put in whatever vector field it put in, but you can put in your own vector field. And it'll graph the vector field. I didn't do the picture of that yet. Then if you come down here, there's a little selection box here. And in fact, you can see what it looks like when I don't have it highlighted. But there's a selection box down here where you have choice. And if I want to see curl, I'll just check curl at a point. All right. So I check that curl. Then what I need to do is check this box that says restrict to 2 dimensions. So I restrict it to 2 dimensions. Then what you do is you just take the cursor and you come over here and you put a spot down somewhere that you want to know about the curl. You want to know about the curl at that point. I did it right here. And what's interesting is that when you're watching the animation, this will spin. Based on this vector field, it will spin either clockwise or counterclockwise. And based on this vector field, it might spin very, very fast or very, very slow. Okay, so where's the curl? The curl is a vector that points in a direction determined by the right-hand rule. And the faster the spinning, the longer the curl vector. And so if you play around with this on the computer, it's kind of fun because you can drop spots in a few places and you can see that some of them spin slowly like this, some of them maybe spin really fast, and so on. Then you go from here and you take off the restrict to 2D button and you'll get this picture. And what you'll see is where I put this dot here, where X and Y were both negative, that corresponds to back here. And so that curl vector would be pointing downward, and it's not very long. That means this vector would be spinning slowly. I put in another one here in the first quadrant, corresponded to here, and you see that it's going up instead of down. So the spin was opposite the direction of that. And it's longer, which means this one was spinning much faster than that. Okay, so that's just to give you a little bit of an idea about curl. We really don't do the physical significance of it so much, but I just like you to understand that there is physical significance. And when we talk about the curl of a vector field, for every point in this vector field, there is associated a curl vector. So if I rounded up all those curl vectors, that's a vector field in and of itself. So the curl of F is also a vector field. So if I came in here and I dropped a bunch of dots, there would be a bunch of vectors here, and just those vectors, not paying attention to the blue ones, that would be the curl vector field. Okay, so you just need to know how to compute them, and if you're interested in this topic, there's lots you can read about it. Thank you.